Good afternoon, everyone. I'm Erota Nurmatova. Today I will talk about transposed Novikov-Poisson algebra and their structure and classification. Definition of transposed Poisson algebra. A triple L is called a transposed Poisson algebra if first L is commutative associative algebra, second L is a Lie algebra. Finally, the two operations are connected by a compatibility condition, which is given by. Now, let us introduce of Novikov algebra. A left Novikov algebra, A is a vector space A cubed with a binary operation, satisfying first right commutativity and left symmetry identity. Similarly, a right Novikov algebra is defined by analogous identities. Now, let us consider the definition of a transposed Novikov-Poisson algebra. A triple A is called a transposed Novikov-Poisson algebra if first A is commutative associative algebra, second A is Novikov algebra. Finally, the two operations satisfy compatibility conditions. These are the following. Both a Novikov algebra with the trivial commutative associative algebra and a commutative associative algebra with the trivial Novikov algebra are transposed Novikov-Poisson algebras. We call such algebras trivial transposed Novikov-Poisson algebras.
Iroda savol bordi. Mana bu yerda demak trivial, commutative, associative degani nima tushunamiz?
Bu yerda Novikov algebrasi bilan o'sha trivial commutative associative algebra bo'lishi uchun
What does it mean, trivial? What does it mean, trivial commutative associative algebra? Iroda?
o'sha lambda x tengi faqat bitta anaqa o'tkazish kerakda.
Trivial means all multiplication is zero.
Multiplication 0, yes.
Trivial associative commutative is the commutative associative multiplication is zero. Trivial Novikov, then for the second one is the Novikov algebra, all multiplication is zero for the second multiplication. And when we say Novikov algebra in this second condition, this is left Novikov algebra or right Novikov algebra?
Novikov algebra.
This is left or right? Actually, this is left Novikov algebra. But we say just Novikov algebra. Okay? Okay, go on.
Next, transposed Novikov-Poisson algebras and transposed Poisson algebras. Theorem. Let A be transposed Novikov-Poisson algebra with a derivation D. This derivation of both algebras, commutative associative algebras and Novikov algebras. Then part A is the transposed Poisson algebra. We are bracket x, y. It's following. Second part B, A is the transposed Poisson algebra where x, y bracket with given derivation. Now let us briefly discuss the proof of part A. It is clear that the anticommutativity condition is satisfied. We will show the Jacobi identity. First, the first term xyz of Jacobi identity, the following. We will rewrite multiplication by the multiplication of Novikov algebras. Similarly, we write yzx and zxy. Next, adding all expressions. So, first, xyz, yxz, and two terms. From the Novikov algebra, we obtained these four terms equality 0. Next, xzy, zxy, and zxy plus xzy. Next four terms from the Novikov algebra, we obtained equality 0. And yzx and three terms. These
So,
are equality 0.
you use the left symmetry, yes?
Left symmetric identity, yes.
Yes. Okay.
Hence the Jacobi identity holds. And we write compare 3-4. A is a Lie algebra. Next, we write compatibility conditions as follows. And the first part, zxy, is equal to the sum of the two terms, and the next part is equal to next two terms sum. This is these terms equal to zxy, and next expressions equal to xzy.
No. The first and last one is zx1. The first one and the last one is equal to zxy.
Zxy. Second.
These two are equal to the second term. Yes?
Yes.
Okay.
3-4. A is a transposed Poisson algebra. Let's continue. In the second part, the bracket is defined using the derivation D. It is obvious the anticommutativity condition is satisfied.
İrada delete koyayım mı bunları? Yeah, okay.
Second part, the bracket is defined using the derivation D. It's obvious that the anticommutativity condition is satisfied. And we consider the Jacobi identity for this multiplication. First term compute x, y, z. First, we affect the outer bracket and then expand the inner bracket yz. And using derivation together with Novikov identities, we obtain the following. We can write
So
the
x, y, z equal to this expression,
this
yes?
expression.
This one,
Yes,
yes?
yes.
Okay.
Similarly, we can write the following terms: yzx and zxy. Now, let's add all the terms. Using Novikov identities, we can so the uh, the x dx dyz
Mm.
dx dyz
Mm.
and dx dyz
Yes.
dy dxz
Mm.
minus dy dxz.
For this four element, you use
For
left symmetric
elements,
identity, yes?
yes.
Mm.
And next, dx dzy and
Mm.
dz dxy,
Mm.
the x dzy
Mm.
and dz dxy.
Mm.
For elements using the left symmetric equal to 0.
Yes.
And d square.
No, and then this. No. If you choose this one, Rhoda, d square y, then you choose this one,
Hmm.
and for this two, you use just right commutativity.
Yes.
And from the right commutator, one of the minus, one of the plus. That's why you obtain these two expressions also is 0. When this one dy dz x, then you should use left symmetry because there's 1, there's 2, there's third, there's where one of them? Here. dz dyx.
Dz
There's four
dyx.
elements. Using the left
Left symmetric
symmetry
identity.
is equal to 0. Okay?
Okay.
And you obtain that the Jacob identity is hold and A is a Lie
Holds and
algebra.
A is a Lie algebra.
Okay.
And next, we check compatibility conditions for the transposed Novikov-Poisson algebra uh, and the following. First, first theorem. At the first theorem equal to two expressions, and second theorem equal to next two expressions. And and dz y and dz y equals qo'shib ayiramiz-da. Dz xy and plus dz
You should
xy
add.
minus.
You should add this one, and minus this one is equal to actually using the compatibility identity for the transposed Novikov-Poisson algebra. These two are equal. Yes,
Yes.
these two are equal actually. Yes.
And the two terms equal to dzxy minus dyzx, and fourth term and last two terms equal to dzyx. Next, the two expressions equal to zxy, and next two expressions equal to xzy. Hence, compatibility conditions holds. 3-4 A is a transposed Poisson algebra.
Okay. So it means that there is two construction from the transposed Novikov-Poisson algebra obtain the transposed Poisson algebra. Yes.
Algebra, yes.
Okay.
Next derivation. Next definition of a right differential Novikov-Poisson algebra. Right differential Novikov-Poisson algebra is triple B, where first B is a commutative associative algebra, second B is a right Novikov algebra, and satisfy the following conditions. Next proposition. Let A be a transposed Novikov-Poisson algebra and B be a right differential Novikov-Poisson algebra. And the following conditions. Then A tensor product.
Right.
Sorry. Is there any difference between this romp, this quadrat operation, and this commutator which you used before?
It is romp right Novikov algebra operation. Romp operation.
It's just right Novikov algebra.
Yes.
In previous theorem, what kind of operation was?
In the previous one.
Yes.
Harfte right differential Novikov.
Oldingi teoremada qanaqa amalida?
The Novikov product. Circle.
Yeah, Majid, this is left Novikov. Yeah, from left Novikov, she gave how to obtain transposed Poisson. Yes.
Yes.
Now she gave right Novikov. That's why she used this multiplication. Это просто обозначение, просто чтобы не перепутать, она left Novikov обозначает через кружочек, а right Novikov обозначает просто через ромбик, чтобы не перепутать всегда.
Понятно.
On the tensor product A tensor B, we define a multiplication and I break it in a natural way using the operations of A and B. Then a tensor product is a transposed Poisson algebra. We now consider properties of transposed Novikov-Poisson algebra. First, we recall the notion of the centroid. Let A be commutative associative algebra or a Novikov algebra. The centroid of A is the set of linear maps such that following multiplication. The set is denoted by gamma A. Now we give a simple remark. For a commutative associative algebra A, left multiplication by a fixed element always belongs to the centroid. Also, scalar multiplication maps Y alpha are elements of the centroid.
Irada, sorry. What does it mean? GA. I don't understand. GA is
GA centroid.
Centroid.
Yes, centroid. We denote it by GA, centroid. Do you understand?
Yes.
Shahla, it means that centroid means, cutting rather. Centroid means all linear maps satisfy this condition. All maps satisfying this condition is called a centroid. It the set of all linear maps satisfying this condition denoted by GA.
Okay, thank you. Understand.
Okay.
Next proposition. Let A be commutative associative algebra and phi in centroid. We define a new operation by composing the multiplication with phi. Then A is a transposed Novikov-Poisson algebra. Proof of proposition. Since phi in centroid, first xy is equal to the following from definition of centroid. Second, xyz equals to xzy. Then the Novikov identities right commutativity of Novikov algebras is satisfied.
Okay.
And third, xyz is equal to following. Next, left symmetry identity satisfies. It is obviously. Finally, the compatibility conditions are satisfied automatically.
Sorry, Irada. Here, in left symmetricity, in left-hand side must be some kind of associator, and right-hand side must be some kind of associator. But here, there is no associators in your last identity which you showed us. So, you see here, it is not associator, yes?
Yes. Left
side?
symmetry identity two associator is equal to will be
Yes. But is it enough for checking left symmetricity? Is these equalities are enough for left symmetricity?
Mirada savol tushundingizmi ama?
Bu faqat mana shuni o'zini tinglasak nol bo'lishi yetarlimi deyapsiz.
Да, Majidxon задает правильный вопрос. На самом деле, вот этот, убери, Majidxon, то, что ты написал.
Сейчас, извините.
Убери. Маршан задает правильный вопрос. На самом деле, left symmetrity это задается через двумя ассоциаторами. Но это раз, вот это два, они дают ассоциатор на самом деле. А вот это раз и два это ассоциатор. Вот это ассоциатор равно ассоциатору. Это одно и то же, если вот это ноль нету, да? Вот равен, вот первые два элемента равен вторым два. Это разность двух ассоциаторов, это же одно и то же на самом деле. Просто вот так написали. Может, вам понятно? Но
Понятно.
почему здесь так написали авторы? Потому что здесь они более сильные условия доказали. Не то, что вот это два слагаемые равно с этим двумя слагаемыми. Они доказали, что это два тоже равно 0, это тоже равно 0 доказали. То, что эти равно 0, это 4, которые less symmetric identity, которые состоят из 4 слагами, выполняется. Понимаете?
Понятно.
Поэтому там
Да,
в середине стоит 0 здесь.
Понятно.
Они просто доказали, это тоже 0, это тоже 0.
Понятно, спасибо.
Дальше.
Finally, the compatibility conditions are satisfied automatically. To zx phi y from transposed Novikov-Poisson algebras two expressions. First term equal to zxy, second term equal to xzy. And next xyz equal to xzy, it's obviously. Then therefore A is a transposed Novikov-Poisson algebra. Next, we present a simple consequence of the previous proposition. Let A be a commutative associative algebra. We define a new operation using the fixed element or scalar. Then the obtained structure is a transposed Novikov-Poisson algebra. To illustrate this construction, we consider a three-dimensional vector space with a given commutative associative multiplication. Using the centroid description and proposition 2.13, we define the non-zero products of the new operation. As a result, we obtain an explicit example of a transposed Novikov-Poisson algebra. Next,
So, Irada, actually, the last example, it is not for the corollary. It is for the previous result. Yes. If you have associative commutative algebra and you have a centroid, using the centroid, we construct a new multiplication.
Yes.
This way and obtain the transposed Novikov-Poisson algebra. Yes.
Poisson. Yes.
Okay.
Next, we discuss the independence of Novikov-Poisson algebras and transposed Novikov-Poisson algebras. A Novikov-Poisson algebra is a triple A consisting of a commutative associative algebra and a Novikov algebra satisfying two compatibility conditions. These conditions describe the interaction between the associative product and Novikov product. This definition will help us compare Novikov-Poisson algebras with transposed Novikov-Poisson algebras. Next proposition. Let A be a transposed Novikov-Poisson algebra, then the following statements are equivalent. Part A, the algebra A is a Novikov-Poisson algebra. Part B is given by following identity. Part C, L operation of right multiplication by the commutative associative multiplication is a centroid of Novikov algebra. And D is the converse. L operation of the right multiplication by the Novikov multiplication and centroid of commutative associative multiplication. Proof of proposition. 4, 5, and 20.
So this proposition connected with transposed Poisson Novikov algebra with Novikov-Poisson algebra, yes?
Yes.
If algebra at the same time is a transposed Poisson Novikov algebra and Novikov-Poisson algebra, then the followings are true, yes?
Yes.
Okay.
Proof. Let's look at the difference between the two forms of B and XYZ. ZXY equal to from transposed Novikov-Poisson algebras identity. It's equal to 0. Thus, condition B holds. Next. Next, first from condition B, we derive that right multiplication operator belongs to the centroid of the Novikov algebra. This follows directly from the compatibility identities after simplifying these expressions. ZXY equal to ZXY, ZXY equal to XZY. Therefore, L in gamma A. Next, assuming condition C and using the definition of the centroid, we obtain Novikov-Poisson compatibility conditions. Therefore, the algebra satisfies the definition of a Novikov-Poisson algebra. Finally, the equivalence between conditions D and B is obtained by direct computation and simplification of the identities. And therefore, D equivalent B, hence the proof is complete. Next, we present the important consequence corollary. Let A be a transposed Novikov-Poisson algebra if A has a unit E, then A is commutative Novikov algebra, and hence A is a Novikov-Poisson algebra. Proof of corollary. The commutativity of A follows from the computation. This implies that A satisfies B in proposition, previous proposition. Therefore, A is a Novikov-Poisson algebra. Next, we consider some important identities in Transposed Novikov-Poisson algebras. Next, let us consider an example of a three-dimensional algebra. We start with Novikov algebra defined on a basis with given non-zero products, and then define commutative associative product on the same vector space. By direct computation, this structure satisfies both the transposed Novikov-Poisson algebra conditions and the Novikov-Poisson algebra conditions. However, the Novikov product is not commutative. Therefore, this example shows that a transposed Novikov-Poisson algebra may also be a Novikov-Poisson algebra even when the Novikov product is not commutative. Next, we consider some important identities in transposed Novikov-Poisson algebras. Proposition. Let A be a transposed Novikov-Poisson algebra. Then the following identities hold. False is following form. Moreover, when the characteristic of the field is not equal to 3, additional identities are obtained. 25.
Actually, Irada, go back please. This proposition is very important because after then, for many results, this proposition will be used. For example, 22, you see, it is very similar to the condition in the definition of transposed Poisson Novikov algebra, but it is not the same, because if you see here, first the Novikov multiplication, after that associative commutative multiplication, and in this case you can change z and y, yes? Similarly to the
Yes.
right commutativity. But in the definition, in the third page, please go on to the third page. Go to the third page. Üçüncü betga o'ting. Boshida. Yeah, keyingisi ekan. Here, in the first, in this condition, the first multiplication is associative commutative multiplication. The second one is the Novikov multiplication. But from the proposition, we have that here you may change the multiplication also. Okay? In this case also, the equality is hold. That's why I would like to give my comment here. And the proposition is 22, yes? If 20, you may go to the proposition now, Iroda. This proposition is very important. Okay?
Yes.
And you will prove it, no?
Yes.
Okay.
Proof. First, identity 22 is obtained directly from the compatibility conditions of a transposed Novikov-Poisson algebra. And after simplification, is obtained.
No, I didn't understand now. I think other participants of the seminars also did not understand the proof of the 22.
X,
Let's
Y,
explain
Z.
it. Yes.
X, Y, Z equal to compatibility conditions of transposed Novikov-Poisson algebras. We will write. And it's equal to first x, z, x, y. A is commutative, from A is commutative, x, z, y.
No.
X, Z, y.
Choose another color. For example, red or green. Yellow is not comfortable to see. Yes.
A is commutative, x, z, y.
Okay.
From transposed Novikov-Poisson algebras identities is equal to x, y, z.
Okay, now I understood.
And second term.
Yes.
These
Just
expressions, equal to y, x, z.
Actually, it is x z y actually.
Y.
But
Yes.
this dot is commutative. That's why it's equal to y x z.
Yes.
So it means x y z equal to x z y. Yes.
Yes.
Okay.
Yeah.
22 holds.
This hold. Okay.
Next, define the operator L equal to hash x. The operator L is a right multiplication by a fixed element. L is a half derivation of Novikov algebra A. By lemma 3.6, for every half derivation phi, it's following form.
But
Next,
you didn't prove now the lemma, yes?
yes.
When will you prove it?
Next, yes, next chapter. We will give next chapter.
In the next chapter, yes.
Yes.
Okay.
Taking phi equals L hash, phi z hash z. X, y, x, y, phi z o'rniga hash z qo'yamiz. X, y, hash z equals x, phi y, hash
Instead of
x, z, hash y.
Actually,
yes, instead of.
Actually, it is
It is by Novikov identities.
H,
Z,
Y, and
Z,
after then Z, yes?
Z, yes.
But
Using the
left
right commutativity,
right commutativity, you obtain this is equal
obtain
to
x,
the
z,
following. Okay.
h, y.
Okay.
Next, instead of next identity, x, y, hash z minus yx hash z equal to hash x hx yz minus hy xz. It is obviously.
Okay.
Let's continue. Using the 24th identities, 24 identities. We rewrite the expression. First, the term is the sum of the two terms. Rewrite first term from the Novikov-Poisson, transposed Novikov-Poisson algebras. This expression to second term equals this expression, and what h this term is cancelled because x z h y x z from right commutativity of Novikov algebra in the y equals h equals y h x y z from transposed Novikov-Poisson algebra identities. H equals it is equals h equals y h equals y z from right commutativity of Novikov algebra. First and third term cancel, and second and last term adding, and 3/2 and fourth and why I still adding because y equals hash this is we will write y equals hash z equal to hash z from Novikov algebra. 3/4 if the characteristic of k is not equal to 3, then 25 holds. Do you understand?
Okay. Next.
Next, we present a classification result for two-dimensional transposed Novikov-Poisson algebra over the complex files. Assuming that the Novik product is non-zero, every such algebra is isomorphic to one of the listed cases. The table shows the characteristic matrix of the Novik product together with the corresponding compatible associative product. Therefore, this proposition provides a complete classification of two-dimensional transposed Novikov-Poisson algebra.
Rather, let's explain what does it mean, this matrix. This one.
T2 matrix.
This 0, what does it mean? This is E1, E1, yes?
Yes.
This is E1, E2, this is E2, E1, this is E2, E2. Actually, the
Yes.
first is just in R case E2, E2 equal to E1.
Yes.
Okay?
E1, yes, E1 is equal to 0. E1, E2.
This is E1, E2,
E1,
this is E2, E1, this is E2, E2.
Yes. And 1.
What does it mean? 1, 1, E1, E1, E1, E2.
E1. Yeah.
Okay?
Okay. E2.
This is clear for everyone. Babacan?
It's clear, yes.
Okay.
Sıra hemen произвольный элемент, да?
Да, hemen произвольный параметры, да.
Параметр. Ага.
Да. Hemen параметры.
Next, we consider the tensor product construction of transposed Novikov-Poisson algebras. Let A1 and A2 be two transposed Novikov-Poisson algebras. On their tensor product, we define the multiplication and Novikov operation naturally using the structure of both algebras. It's following. Then tensor product is transposed Novikov-Poisson algebra.
Ortaya kaçındı.
No.
Anne. Hadi gel.
Şimdi.
Ha şimdi. Böldü.
Now we present a construction from non-transposed Novikov-Poisson algebras. Lemma. Let A be a transposed Novikov-Poisson algebra. Define a new operation by adding a scalar multiple of the associative product. Then A is a Novikov algebra. Proof of lemma. We check the right commutativity. First, x, y, z. First operation affect x, y plus px, y. Next, second operation affect. It's following. And x, y, z from the right commutativity of Novikov algebra equals x, z, y. P x, y, z equals transposed Novikov-Poisson algebras identity equals x, z, y. X, y, z. Px x, y, z equals from transposed Novikov-Poisson algebras x, z, y plus p quadrat x, y, x, z, y. Next, first bracket equals x, z, x new operation z and affect y. Affect y. Next, x equals x, z, y. Yes, right commutativity holds. Let's continue. Let's
Dawson.
continue. We will show left symmetric, the symmetry identity. We expand x, y, z. This term using a new operation. First, we apply the operation to the first bracket. Next, we apply the operation again. Get the following expression. Similarly, the following three terms are also considered the same. Next, we can write the right and left sides of left symmetric identity. First, x. First, x, y, z minus x, y, z. Next to expression. For term is equal to 0 from left symmetry of Novikov algebras. Next, p x y z and x y z, p x y z, it's equal to 0 from Novikov-Poisson algebras identity. Şu an ko'rsatayapmi Novikov-Poisson algebras identity.
Why is this equal to
Hepsi bor
0?
edi. 0.
Why? This is
Because
just x, y,
y, z
yes.
equals x, y, z. From Novikov-Poisson algebras identity.
Novikov-Poisson.
Hazır. X, Y, Z.
X, y, z, yes.
Yes, X, Y, Z equals X, Y, Z. And
Okay.
next identity using. We will next identity using.
But please go to the lemma or proposition. Bir bet qayting orqaga. Bir bet qayting.
What?
So you have transposed Novikov-Poisson algebra. When you use the Novikov-Poisson, I didn't understand. A is a transposed Novikov-Poisson algebra, yes?
Novik.
One, why you use a Novikov-Poisson identity? That's why I didn't understand.
Novikov-Poisson.
Please go to the proof. Yes. This 4 is okay. Last symmetry is hold.
Yes.
Then P, X, Y, Z.
X, Y, Z. Declaration cancel bo'ladi. Two terms. Because A is commutative associative algebra. It's cancelled. X, Y, Z. Buni X, Y, Z'ni bunaqa yozsakchi. Endi Z, X, Y, Z. Bu Z, X, Y. Inverse.
So here, first identity of Novikov-Poisson, yes.
Savolingiz nima edi?
Shu yerda o'sha birinchi ayniyat qo'llanilyaptimi? Shu nol bo'lib qoladi-da hozir.
O'shani qo'llamayapmiz. Qaysi nol bo'ladi?
Mana shu qo'sni almashtirish emasmi? Novikov-Poisson. Ko'paytmalar joyida, yo'q, ko'paytmalar almashib qolibdi-ku.
Mana bundan Transposed Novikov-Poissonni qo'llasak bo'lar ekan. Menimcha shundan bo'ladi mana. X, Y, Z from Transposed Novikov-Poisson algebras identity equals X, Y, Z plus Y, X, Z. Minusligi uchun bu yoqqa minus.
But there is two should be.
Cancel.
2 bo'lish kerak-ku yerda Iroda.
Yarimmi?
When you use the transposed Poisson, there is 1 to 2 should be.
Bir taqsim chiqsak. Y, X, Z.
But I remember you checked it, I think. You proved it. Why you don't have the proof here now? You proved it completely. Okay, you will check it now. Then, okay?
Yeah.
Now we will leave it. But it should be true. This two expression equal to this one. Within the left symmetry and compatibility. Maybe you should use proposition 220. Please go on 220. 220.
220.
220. What? Maybe you will use this one. Okay? Or this one. Okay. Next. So what does it mean? Lemma. Lemma 224. Please go to the lemma again. So what is it? From the transposed Novikov-Poisson algebra, considering the sum of two multiplication, sum of two multiplications. Even here P, you obtain Novikov algebra, okay? The meaning of the lemma is the sum of two operations give us the Novikov algebra. Okay?
Okay.
Next.
Theorem. Let A be a transposed Novikov-Poisson algebra. Then for any fixed elements P, Q in A or scalar, define new operation. Then the triple A is also a transposed Novikov-Poisson algebra. Proof first.
Here also I would like to give some comments. For example, John knows that from the associative commutative multiplication, using P, obtain new associative commutative multiplication. Yes?
Multiplication. Yes.
Here, from the sum of two multiplications, we obtain new one, and it's also proves that Novikov-Poisson algebra. And the theorem says that these two operations, the first is commutative associative, the second is Novikov, give us transposed Novikov-Poisson structure. Okay?
Okay.
So let's prove it.
First, it is straightforward to check
No,
that remains
this one
commutative
is
and associative.
easy. It is obvious. Everyone knows it.
Yes, A is a
That's
Novikov
why-
algebra.
Yeah, you
By
already
lemma.
by lemma you already proved this is Novikov. You have to prove
A
the
is Novikov
compatibility conditions.
conditions.
Yes.
Now we
Okay.
check the compatibility condition. First, we effect the first operation, then the second operation. It's following. First pxy, second operation affect pxyz plus q pxyz. And px from the transposed Novikov-Poisson algebras identities, it's this theorem equals pxzy plus q. It's commutative associative algebra. From commutative associative algebra, we write following. Next, it's equal to x, z, y. Hence, first compatibility conditions is satisfied. We check the next compatibility condition. We effect again the first operation, then the next operation, and for this theorem equal to these expressions from transposed Novikov-Poisson algebras plus next theorem, and the first two terms give zxy, and next two term give us xzy. Therefore, second compatibility conditions holds. Hence, A is given with new operations becomes the transposed Novikov-Poisson algebras. Next, we counter product. Let Vn be an n-dimensional vector space and denote by Un the space of all binary operations on Vn for a fixed element U in Vn and any two binary operations A, B in Un. We define a new binary operation A, B, U on Vn by setting following form. AB U is called the left counter product of A and B.
What's the U here? Are there any condition for U? Any fixed element, yes?
Fixed, yes.
Okay.
Next proposition, let A be a transposed Novikov-Poisson algebra and U be a fixed element in A. Then then a new operation is a Novikov algebra. First, commutative associative algebra and Novikov algebra from binary operation is a Novikov algebra. And second operation with operations A is an associative commutative algebra.
Please go back to the counter product again. So counter product means if you have two multiplication A and B for the fixed element U, from A, B, U, you obtain new product. For the elements X, Y, it defines for the following way. Okay? Now, in the following theorem, please go to the theorem. You know the theorem. Okay, kaç bitmiş ki? So, proposition, in the following proposition, there is two multiplication we have, associative, commutative, and Novikov multiplications. And from these two, using the counter product structure, you can obtain the first multiplication. It means the first is commutative associative, the second is Novikov. But if you consider the inverse, the first is Novikov, the second is commutative associative, it is another product. Actually, if you consider like this, you obtain Novikov algebra. The inverse give us associative commutative algebra. Okay, let's prove it.
Proof. Firstly, we define operation x, y and new differentiation and new operations.
New multiplication.
Then we obtain x, y, u x, y minus u x, y minus x, u, y. And it's equals to following it's equals to minus x, u, y, and from transposed Novikov-Poisson algebras, it's equals to minus x, y, u. And we define next operation, new operation x, y. We denote xy minus uxy minus xuy. It's equals ux minus uxy. We define, we check the commutative associative xyz from xyz. It's equals to from simplifying xyz. And therefore A is the commutative associative algebra.
Hmm. And the second one.
And first we apply the new operation xyz. We write xyz new operation to the first bracket, and then we apply it to the second bracket, and using the transposed Novikov-Poisson
İroda
algebras.
kursoriz aytmoqchi bo'lgan joyida tursin, boshqa joyda turibdi-da. O'sha mana birinchisi bu. Keyin bundan buni hosil qilamiz. Bundan buni hosil qilamiz. O'sha joyda tursin kursor. So, after then
uxy commutative. So xyu is equal to xyu, and from transposed Novikov-Poisson algebras equals xyz. Then it's equals xzy.
So it is right commutativity is hot, yes?
Right commutativity holds, yes.
Okay. Now you have
Yeah.
to show left symmetry.
Y.
You
show left symmetry
Kursor o'sha
identity.
tepeda tursin.
We define yxz as
Yes.
follows. And we write each theorem by substituting it.
So
For the
xyz, yxz,
xyz, and yxz.
So xyz is equal to this one.
Yes.
This y is the same with this, yes?
Yes.
Or this one? Which one is you use?
Yxz, it's similarly xyz. X instead of y instead of x.
Okay.
Z, yxz.
Okay.
And yxz equals to y.
Last one. Okay.
Last one. And xyz is similarly.
Similarly, is here. Okay. And
Yes.
then
and for the we apply the compatibility identity H theorem from transposed Novikov-Poisson algebras. First theorem is equal to this expression. Second theorem.
Okay.
First. And
the second one.
Second.
Okay.
Third.
The first one. Okay.
First. And first uxyz plus third theorem yxz equals uxyz.
Okay.
From Novikov algebras write commutativity. So this term cancel.
Okay.
And
We obtain the six,
We-
eight,
yes.
6 element, yes?
6 elements, yes.
Yes. After that,
Let's continue. Next, from the two these expressions using the left symmetric identities. Yeah, from first
what is this?
and yeah, and next second and fourth.
No. The
No,
fifth, where you have ux. Yes.
Yes, we define follows. We get following.
Then,
You were first term and u equals y z. U y u equals
you can change y and x, yes?
y, yes,
Okay.
y z from Transposed Novikov-Poisson algebra. It's cancel. And next, this term ux y z. We apply the compatibility condition again for these two terms. First, next one, 2.
Madam.
Yeah.
I didn't understand here. What did you do? It is just you will change y with x z. You will change y with x z. You will change here. X with y z. You will change here. Nothing to do. There is nothing. Just you will change these two elements. Then after then you will use the condition because you have u x z, u y z. Here you will choose the compatibility condition for the transposed Poisson Novikov algebra. Okay?
Butane the
Up.
first from Transposed Novikov-Poisson algebras identity first equals to this expression and 2 equals next expression and u next uz t'yi belgili olamiz uz t'yi from left symmetric identity these expressions equal to y equals t minus x y
T.
Use it, yes.
T.
T, yes. T is
T.
a
Yes.
use it,
T.
yes.
T is a use it.
Mm.
Next, we obtain following
Mm.
from proposition 2.20. XY. This
This
is
is equal to 0,
equal
yes.
to 0.
Okay,
From A is a Novikov algebra.
okay.
Next theorem, let A be a transposed Novikov-Poisson algebra and U be a fixed element in A. Then A is all A with binary operation counterproduct is also a transposed Novikov-Poisson algebra. Proof of theorem: denote counterproduct. By the definition of transposed Novikov-Poisson algebras, we obtain 2zxy. It's following. Next, A is commutative associative algebra, so it is equals to following. Equals from transposed Novikov-Poisson algebra from compatibility condition, it's equals to this expression. So first term equals to zxy, and second term equals to xzy. And next identity, we check next identity, xyz equals to following, and xyz from transposed Novikov-Poisson algebras equals xzy. This term equals xzy. Two compatibility conditions holds. Therefore, A is a transposed Novikov-Poisson algebra.
Understand?
Do you understand? Thank you for your attention.
That's all?
Yes.
Ну, хорошо, я просто хочу отметить вот этот proposition 2.27, есть же? Откройте еще раз. Предыдущее предложение. Вот это доказательство на самом деле отличается от доказательства, который архивный вариант из статьи, потому что Ирода сама узнала то, что там доказательство не очень-то корректно, потом мы записали авторами. Они потом исправили. То, что сейчас Ирода рассказала, это исправленный вариант доказательства. А в архивной версии там не очень-то корректно написано доказательство, там не сходится.
Очень круто.
Да.
Понятно.
Ну, на сегодня все. Сейчас половину рассказала Ирода, а в следующий раз будет продолжение. Надеемся, что до конца будем успеть в следующий раз. Вопрос есть?